Okay, good. So, finally. So, today got an email that the final is actually scheduled for the final exam is scheduled for December 19, 6 to 8. Previously, it was something else, the December 12. So, maybe this will still change. I don't know. It's always funny here. And it's at 0600 to 0800, and I hope that's PM. But I will reconfirm.
So it's the 19th, not the 12th.
That's what it looks like, but like take it with a pinch of salt. I need to like double check with them. Even simple things here are more complicated than you would imagine. So on Monday I'm not gonna be here, but I will have my postdoc to take the class. I'm visiting Princeton, but for you it's business as usual. So there will be someone else. So what we are gonna do today is we're gonna look at general linear systems where the matrix can be rectangular. So we are not making any assumptions about niceness of the matrix anymore. And this will lead us to studying vector subspaces, because you will see that the general linear systems are a little bit more funny. And vector subspaces will naturally appear there and will actually help us characterize all the possible solutions that happen. All right, so you remember, actually you have been just coding that, right? You have just been coding the solve for this simpler case. That's what we studied the last time. So the simplifying assumption was that the matrix was square, was n by n. And for an arbitrary right-hand side, you now know how to solve that, right? Using Gaussian elimination or equivalently LU decomposition. You know that there are these tricks, right, like partial pivoting, that help it. So today, and maybe next time also, we will discuss the case, what if A is not a square matrix? What if it's a general rectangular matrix? And it turns out that we can simply extend the Gaussian elimination. Gaussian elimination is a very powerful idea and will apply to this case as well, except that there are some special cases. So we can either be talking, there are two types. If you are talking about rectangular systems, they can look either like this. Good to keep this picture always in mind. So this is my A, this is my X, this is B. So this is the case of like short and fat matrix. It has more columns than rows. Or there is also this other case where it's like tall and thin matrix, when it looks like this. This is my X now. This is AX equals B. It's always AX equals B, except that the interpretation depends on whether there is more columns than rows or more rows than columns, like here. And if it happens to be square, that's exactly what we covered previously. So, well, let's start with a simpler case. So let's assume first that the B is 0. Oh, by the way, I don't need to comment that these dimensions have to agree, right? This number of columns has to be the same as the number of elements in X in both cases. And here the dimension of B is the number of rows of the A matrix all the time. That's just a matrix vector multiplication is just a special case of matrix multiplication, where this just happens to have just one column. You should know that by now, right? So let's first take a look at the special case where B is 0. Turns out in this case it's not only it's a simpler case, but it will also be like a building block for the general case. So if we have this system and we want to find all the solution AX equals 0, what we will do, we will perform elimination, and we will convert the matrix to what's called reduced row echelon form. There's a row echelon form, and even simpler and more useful thing is the reduced row echelon form. I'll explain it in a second. So you can immediately notice one thing about the system AX equals 0. So 0 means 0 vector of all zeros of the appropriate dimension, right? There is only one dimension actually fits it. And A is an arbitrary matrix here. So So you can immediately notice one thing about this system. What do you immediately notice? Can it happen that it doesn't have a solution? It's impossible, right? It always has at least one solution, because x equal to all zeros will be always solving this equation, right? No matter what is in A, if my x's are all zeros, I will have a solution, right? The question is, if there is just this one solution, it's really boring solution, right? Like all zeros, every time it's gonna work, not very exciting. What we are interested in, if there are some non-trivial solutions, some solutions that are not all zeros. That's something that's not for granted, right? Sometimes it might happen, sometimes might not happen. And the way we find out is by doing elimination on that matrix. So let's take a look how elimination works on a general rectangular matrix. So starting with this example. So I have a matrix like this, and I will just do the standard row eliminations. That's what you know probably better than me at this point, because we're just coding it. I hope we're not doing it this afternoon. Oh, I should mention there is another project posted, project number 3 on applying linear systems. You might have noticed it already. You know the drill is going to be again next Friday. And I am hoping that you have already done the previous project. It was actually implementing the Gaussian elimination for square systems. So let's apply it to this system. So we take first the first row and use it to eliminate these things here. These two elements. So I multiply this here. I multiply this by -2 and add it to the second row, right? So if I multiply it by -2, I get -2 plus 2, that's 0. -2 plus 2, that's 0. Here we get -4 plus 8 is 4. -6 plus 10 is 4. So this is elimination applied to the second row. Then the third row, so I multiply this now by -3. So I get -3 plus 3 is 0. -3 plus 3 is 0. -6 plus 10 is 4. And -6 and -9 and 13 is 4. Right? So this was the first step. Now you can notice that here, now we are moving to this part of the matrix, right? We are sort of like done with this. Now we are moving here, but here, there I have 0, so there is nothing I can do. So I move further down. I move to this column here, and here I can eliminate, right? Here I can easily multiply this row by -1 and add it to the last row, right? It's 4, so it just cancels the last row, obviously, and I get this form. And this would be the row echelon form. And if I want to bring it to reduced row echelon form, I can notice that I can do some further simplifications here. In particular, I can take this row, the second row, and eliminate this element here using the second row, right? How do I do it? Well, I multiply it by -2, right? And add it to the first row. So here I will get -2 plus 2 is 0, and -2 plus 3 is 1. And here are zeros, so nothing happened here. And this is what's called the reduced, so this is the final form. It's called the reduced row echelon. So how would it look like in general? In general, what you can always bring an arbitrary rectangular matrix to is the row echelon form looks like this. So I have some, let's see. I have some non-zero element here, and there might be in general non-zero elements following it. Then there are some zeros, but then are again some non-zero elements. It could also be like this. It's like the general, and there can be also arbitrary number of rows full of zeros, right? So this is an example of a row echelon. These x's just mean that there can be any numbers of the zeros, so that there are zeros. So it means that it's like a staircase pattern, right? At some point there are just zeros beginning with. Has to be at least as many zeros as in the previous row. And at some point there is a non-zero, and after that there are all non-zeros. That's the row echelon form. And the reduced row echelon simply means that these elements we can, the pivot elements, we can turn to ones, right? That's because these the pivots had to be non-zero, so we can divide the entire row with it, right? And if I do that, then I can do this type of elimination going up, and I can zero these elements here too. So the reduced row echelon, could I do it nicely? So here is 0, 0, 1. It's gonna be 0, 0, 0, 1. This is just to give you like a graphical idea how the reduced row echelon matrices look like. And here I can be arbitrary number of 0 rows. So this is a row echelon, this is a reduced row echelon. So in the reduced one you have the pivot elements are all 1, and I have eliminated everything that was above them, so these become zeros. And I can always do that, obviously, right? The elimination is going to work. So to summarize this, the row echelon form always brings matrix to such a form. So unit pivot elements and zeros above and below them. So the pivot element is the first in every row. The pivot element is the first non-zero. In the reduced one, it's actually always 1. And then in the corresponding column, it's the only one there. The rest are zeros. Yeah? Now here my x actually means 4, x1, x2, x3, x4, 4 coordinates, right? And the multiplication is like this. This is x1, x2, x3, x4. And these, the coordinates corresponding to the pivot elements are called pivot variables. So here in this case, x1 and x3 would be pivot variables. And x2 and x4 would be free variables. The idea is that now I want to do like the analog of back substitution. But here I have like a lot of freedom, right? Because here the solution is not uniquely determined, as you can probably already sense from this. And I'm trying to characterize all the freedom I have in picking the solution. As we already said, like the solution all zeros is always a solution. But we want to characterize how all the possible solutions look like. And the idea is to essentially do something like back substitution after we fix the free variables. Because the idea is that the free variables, we can pick whatever we want, and then we can solve for the pivot variables. I guess that's why the free variables are called free variables at the first place, because you can just plug there whatever you want, and for whatever you want it, you will uniquely determine x1 and x3, because they are the pivots by back substitution. And so let's try it in this example, how exactly that works. So again, this x was like x1, x2, x3, x4. And this is sometimes called the homogeneous system, when the right-hand side is 0. And we want to find all the solutions of the system. These are called also homogeneous solutions, or linear combinations of special solutions. So how do I do it? So I said that these x1 and x3 are pivots, and x2 and x4 are free, right? So that means that I can pick them arbitrarily and compute the x1 and x3 out of it, right? So why don't I pick, for example, so first I can pick x2, let's do it the same way as I did it here. x2 I can pick as 1 and x4 as 0, right? Why not, right? So let's try to do this and compute what the corresponding x1 and x3s will be. So from the second equation is x3 plus x4 equals 0. Because x4 is 0, that just means that x3 is 0, right? So I'm now basically doing back substitution here with this special choice of the free variables. So now I know what is x2, x3, and x4, and I plug it into the first equation. The first equation says that x1 plus x2 plus x4 is 0, right? But x4 is 0 and x2 is 1. So this says that x1 plus 1 is 0, which means that x1 is clearly minus 1, right? So the first special solution is minus 1, 1, 0, 0. Let's check that this really is a solution. It's always good to check, right? And obviously, if you multiply this matrix with this vector, you can see that this really is a 0 vector. So I did not make a mistake right now. I might make a mistake later. Always check it just by substituting that. So this is like this is an interesting solution, right? The 0 solution, of course, it's always going to work. Right? Who cares? But this one, that's not always going to. This works for this particular matrix. That is interesting. That's telling us something, right? So I can pick anything for x2 and x4, right? If I, for example, picked like x2 being 2 and x4 0, that would be dumb, right? Because I wouldn't really get anything new. If I want to get something new, and I will formalize these new in a little bit when we talk about linear independence, I can pick this, right? This will be another interesting solution. So let's take a look at what I get in this case. So in this case, I have again x3 plus x4 equals 0, which in this case is x3 plus 1. So that means that x3 must be minus 1. I think. That's right. And then the first equation is again x1 plus x2 plus x4 equals 0. x2 is 0, x4 is 1, so that means that x1 has to be minus 1. So the second one I have is minus 1, 0, minus 1, 1. I'm just putting together x1, x2, x3, x4, right? So let's try it, if it works. So if I get, I guess, 1 minus 1, and 1, that's fine. And this is also fine. You can see that the last row is satisfied no matter what, right? So these are my two special solutions. This is exactly here. That's what they are, and they are two because I have two free variables. I can write all the solutions of this system in this form: alpha times the first one plus beta times the second one, where alpha and beta are just arbitrary two scalars. You can see that I can pick zeros, in which case I have the trivial case of zeros there too, right? And this completely characterizes all the solutions to this system. So remember, the trick is that the free variables I can choose is if I have n free variables, that means I have n of these special solution vectors. And then this is a linear subspace, or vector subspace. This is what we will formally define in a little bit. And this is the solution space to this homogeneous system of equations. And all you need to do to compute this is reduce the matrix to the reduced row echelon form. Okay? Is that clear? So, in the general case, when we have a non-zero right-hand side, we can again apply the same thing, and I have one example to show you how it works. And we can again reduce it to the row echelon form and then check if a solution exists. So if we have a non-zero right-hand side, we don't know if it has a solution or not, right? It might have a solution, it might not. Like the 0 is not going to do the trick, right? The b might be arbitrary, the b might be non-zeros, so we don't know just by looking at this if there is a solution at all, right? But what we do know already is that if there is a solution, it can be written in this form. It can be written as the particular solution, which is just one solution, And then this sum of alpha k xk, that's exactly what I wrote on the previous example. That's the space of all the special solutions, all the solutions of the homogeneous system. Obviously, if I take any of these, if I take the sum of alpha k xk, then they have the property that a times sum of alpha k xk is 0. So obviously, if a xp was giving me b, then a xp plus sum alpha k xk, those are vectors, will give me b too, right? So these xk's are the vectors that will multiply with a give me 0, and the xp is the one that gives me b. So this is, I sort of like decompose the problem into two sub-problems. First is defining the particular solution, and the second is like determining what sort of leeway there is, what variability is it, what other, how all the other solutions look like. So in the special case, if there are no free variables, if we have the maximum number of pivots, then this is nothing. This is just a 0 vector, and the solution is unique. Just the particular solution would be the solution. In the general case, there are some free variables, and then we have like an infinite number of solutions, and all the solutions can be characterized like this. So that's the general case. Maybe I will do one example, because there is still the question, how do we tell if it even has a solution or not, right? And the way we tell is, again, just by using the Gaussian elimination, just by reducing the matrix to the reduced row echelon form. So let me do an example to explain this. So if I now have a general system, ax equals b, and I'll explain it on this example. So let's take a system 1, 3, 0, 2, 0, 0, 1, 4, 1, 3, 1, 6. And this is being multiplied x1, x2, x3, x4. And I want it to be equal to 1, 6, and 7. So this is my b vector. So the idea is to apply the same reductions on both the system matrix as well as on the right-hand side, just like you were doing with squares in the square case. So one way we can look at it is so this is our A, this is our B, and this is of course X. So one way you can look at it is by forming an augmented matrix, A and B. So in this case, the augmented matrix, it's very simple. I just copy the matrix. Oops, this was supposed to be 3. Copy the matrix A. And append the right-hand side here, right? The idea is that any operations I'm performing on the rows, I'm then automatically performing also on the right-hand side, right? Because the systems can be rectangular, I can as well add another column. Nothing changes, right? So let me do this. Let me apply the elementary row operations to reduce this to the reduced row echelon form. So the first row stays unchanged, right? Here the second row is fine because I have 2 zeros given to me to begin with. And I will eliminate the third. I will eliminate these guys here by adding -1 times this row. So this will give me 0, 0, 1, 6 minus 2 is 4, and 7 minus 1 is 6, right? I can eliminate again, so this time I can eliminate this whole last guy by adding -1 the second row. So what I will get is this. 0, 0, 1, 4, 6. I just copy that, and the last row completely disappears. So what that means is that this system got reduced into the following reduced row echelon form. Now I split it back into the system and the right-hand side. So this is my x1, x2, x3, x4, and this has to be equal 1, 6, 0. So what do you think? Are we, yeah?
So at this point it happens that all of our pivots are 1. If they weren't, would we...
Right, correct. If they weren't, we would just divide by that, right? I just made it simpler here so I don't have to divide.
Okay.
They wouldn't, right? There could be like anything to begin with, then I would just divide with it. So if they are not 1, I can make them 1. That's the point of the reduced row echelon. Good question, thanks. So this is my reduced row echelon form, and what do you think? So in general, in a system like this, I can not have a solution, right? Or have a solution or infinitely many solutions. So like the first, okay, is there a solution? So do you think, am I in luck here? Do I have a solution or not? In this case, I'm in luck. There is a solution because the last row says nothing, right? It just says 0 equals 0, which is always true regardless of what the values of x's are, right? So the last row as well would not have to be there. Could as well take it out, right? But for example, imagine there wasn't 7, but there was 8 here. What would happen? Actually, I can just do it, right? What would happen here? I would have 8. Here I would have 7 because here I subtracted once, and here I would have 1. So here I would want this to be 1, right? In this case, what do you think? Solution cannot exist, right? There's no way how you could multiply 4 zeros and get 1 out of it, right? So really it depends on the right hand side if the solution exists or not, and the reduced row echelon will tell you that. If it happens, then the last rows that are all zeros have zeros on the right hand side as well. That's okay, and we have a solution. If it happens that these 0 rows want something non-zero, there's no way we could have a solution. So this is how you can tell if there is, yeah?
The non-zero has to be the last column?
Yeah. We are talking, yeah. There could, in general, if I had like a larger matrix, there could be like more 0 things. So column, yeah, the right-hand side, yes.
Okay.
Yes, that's what I was talking about. And the coordinates of the right-hand, or the elements of the right-hand side that correspond to these 0 rows, right? So this is how you can tell if there is a solution or not. I don't know, shall I continue with this example and then find? So this way we can, oh yeah, I should totally finish that. I mean, it sounds simple to me. I don't know if it's boring or not. So how does the solution look like? So this is not there. This is this, and let's put back there the 0. So we have the case. So let me do it again. This was the original example where we actually do have a solution, right? Then the next logical question is what the solution actually is, right? So can you tell me that before I'm finished writing? So how do we find the solution from this? Now we know there is 1. So again, we have some pivot variables and some free variables, right? The free variables are x2 and x4, and the pivot ones are x1 and x3, right? The x1s, the first column is a pivot, and the third column is a pivot. So for the free variables, I can pick whatever. So why don't I pick just zeros, right? So what do I get if I pick x2 equals x4 equals 0? What do I get? From the first equation, I get that x1 equals 1. And from the second equation, I get, because x2 and x4 I said is 0, x3 is 6, right? So this actually is, so if I expand it with 0, so 1, 0, 6, 0, this is my particular solution. Let's test it to make sure I'm not fooling you. 1 and 6 is 6. Yeah. So I'm just multiplying this with the matrix to make sure this really is a solution to that. And this is 1 and 6. Yeah, is 7. So this indeed is one solution, right? Everybody agrees? So the idea was to, again, do like a back substitution, where for the free variables I can pick anything. I could pick other numbers, but zeros just happen to be the easiest numbers to compute with. So that's a nice particular solution. And then I just perform back substitution. Make sense? And if I wanted to find the set of all possible solutions, then the next thing I have to do is to solve this, the homogeneous system, right? So exactly the same thing except for the right-hand side being all zeros now. Maybe I can just show what it is here, and then not do all the, because we already have the reduced row echelon form. That's this, right? And we know that x2 and x4 are free variables. So how do I get the special solutions? So I pick x2 equal 1 and x4 equal 0. And I'm solving. Why don't I want to pick x2 being 0 too? Because then I would just get a trivial solution, right? And I'm not interested in that. So for this solution, it turns out that what I get is -3, 1, 0, 0. I'm a little bit cheating here because I don't want to waste all the time. Just showing you how do I plus 2, 2 minus 5. And the second case is if I pick x2 being 0 and x4 being 1. In which case I get -2, 0, -4, 1. So this is the x2 is 0, x4 is 1. Here x2 was 1, x4 was 0. And these numbers, these correspond to the pivot variables, and these I compute simply by back substitution, taking the special case. So the set of all solutions of the system can be written like this: particular solution plus x2 or alpha or whatever, really, right? That's a free variable, plus x4 -2, 0, -4, 1. So any solution looks like this for all x2 and x4 scalars. So this is now it's completely solved. There's no questions left. All the solutions of the system have to look like this and exactly like this. So I pick arbitrary x2, arbitrary x4, and I have a solution of the system. Okay. So let's summarize this. In general, if I have an arbitrary system, rectangular, it doesn't even matter if it's like short and wide or thin and slim. So there are two possibilities. There's either is a solution, solution exists, or solution. Sorry, the solution either doesn't exist, or it exists, right? If it doesn't exist, that's it. And if it does exist, then there is either that one unique solution, or there is infinitely many of them, right? And how do we tell? We tell by looking at the free variables in the reduced row echelon form. So if there are some free variables, there must be an infinite number of solutions, because I have these special solutions, and then any scalar multiple of that special solution will give me another solution. So I can pick infinitely many solutions. The only exception is if there are no free variables, then there is just the particular solution is the only one. I think these cases are not really so different, because this is just adding a subspace of dimension 0, but yeah, whatever. Cannot hurt to think about it this way. Okay, so some basic concepts very closely related to solving systems of linear equations. So what is a rank? I think I was already talking a little bit informally about rank of the system. So we are talking about a rank of a system or rank of a matrix. And the rank will be defined as the number of pivot elements after we do the reduced row echelon form, or row echelon form, doesn't really matter. The number of pivot elements is the same. And it's usually denoted as lowercase r. Now one thing you can notice is that regardless of the shape of the matrix, be it either this case, where we have more columns than rows, or this shape, the rank has to be less than or equal the smaller number of the number of rows or number of columns, right? That's because the number of pivot elements, at most, I can have them, in this case, I can have them at most as the number of rows, and in this case, at most, the number of columns, right? So it always has to be smaller than both m and n, so it has to be less than or equal than the minimum of m and n. M is the number of rows, n is the number of columns. So because we define the rank as the number of pivot variables, then the free variables is the rest, right? So the number of so if we have n columns and r pivot variables, then the number of free variables is obviously n minus r. The rank is closely connected to the notion of inverse matrix. And here is how we can tell if a matrix actually is invertible. You remember that I was always saying that matrix, so first of all, about invertible matrix, we talk only in the case it's a square matrix, right? We don't define invertible rectangular matrices. There are like pseudo inverses and so on, but that's an advanced thing. And how do we tell if we have a square matrix? How can we tell if it's invertible? The easiest way to say that is by looking at the rank of the matrix. So if the rank is exactly n, if the matrix has full, the maximal rank, then the matrix is invertible. Also, once the matrix has full rank, that for arbitrary right-hand side, there is a unique solution, right? Simply because I can invert it and solve it. And the homogeneous system of equations has only the trivial solution. And this also implies that we have an invertible matrix, then the reduced row echelon form is going to be just simply the identity matrix. So here we are playing like no games, there will be some non-zero elements and bunch of zeros, nothing like that. It's just beautiful, clean identity. Now there are two special cases which are worth discussing explicitly. So let's look at the full column rank case. So now we are talking, here on the slide we'll be talking about matrices which have more rows than columns. So this type of matrices, more rows than columns. So it's a tall and skinny matrix. And we say that this matrix has full column rank if the rank is equal to the number of columns, if it's the maximum possible rank, right? We know that the matrix cannot have higher rank than the number of columns. So if it is exactly the number of columns, it's full rank, right? It wouldn't have to be full rank. There could be some zero columns, in which case we would not talk about a full column rank matrix. So if we have a full column rank matrix, then it means that the reduced row echelon must look like this. Right, and here are zeros everywhere. Here are also zeros everywhere. So it means that all of the variables, so the variables, this would be the vector of variables, right? If we had like a linear system there, our axis. So all the variables are pivot variables. There are no free variables whatsoever, right? So what that means is that this system has either no solution or unique solution, because there is no leeway. There are no free variables, so there will either be one or no solution, right? There cannot be more, because I don't have any free variables. I don't have any freedom to choose. Also means that if the b is 0, if I have the homogeneous case, that's only solved by the trivial solution by x equals 0, right? Okay, so let's look at the closely related case of full row rank. So now let's consider the other type of matrix, so the short and fat matrix, which is a matrix that looks like this. So it has n greater or equal than m, so it has more columns than rows. And in this case, we talk about full row rank, right? And the full row rank is if the rank is maximal, if the rank R is equal to the number of rows. And again, the idea is the same. That means that all of the, it has all pivot entries. All of the rows have pivot entries. There is like no 0 rows at the end. So it ends with 1 here. And then if we assume that this is a full rank matrix, that means that this the system of equations ax equals b. So here x would be like this long thing, and b would be this shorter thing. Ax equals b always have to have a solution. That's because we don't have any free variables, so we can always, by back substitution, we can always find the solution. We can always pick these x's. And unless this happens to be square, so if we are assuming this really has, so if n is strictly greater than m, there will be always an infinite number of solutions, because there are here in this case there are free variables. All these things all these variables are free variables. So this system has infinite number of solutions. Yeah, the number of free variables is exactly n minus r. So if n is strictly greater than m, then n minus r has to be at least 1, right? So in the language of linear systems, this corresponds to the case when the linear system is underdetermined, right? We are solving for like a bunch of x's, lot of x's, but we have a small number of equations. Right. So in this case, some of these x's are free. This linear system is sometimes called underdetermined. If it's full rank, there always has to be a solution, and there will always be an infinite number of solutions if it's really rectangular. In this previous case, the full column rank, this is sometimes called overdetermined, because if this is like a system, overdetermined, that means that we have more equations than we have unknowns, right? So that means we need to be lucky so that there is a solution at all, and if there is a solution and the column rank is full, the solution is unique. So we are like barely lucky if we have any solution at all, right? It's because here we are asking more than we have degrees of freedom, which sort of intuitively makes sense, right? Those are the things in the axis, those are the things you can pick, and those are the things you want. And if you want more things than you can pick, then clearly that doesn't usually go well unless we are lucky, and it just happens that these equations are actually combinations of each other. Oh, no. Sorry. It depends on the right-hand side. Right. Okay. So just like when we were doing the Gaussian elimination and I was deriving the LU decomposition, the same thing can be done for reduced row echelon form. So all these simplification operations can be represented using matrix multiplication. And the matrix multiplication encodes these special three types of elementary row operations. So it's either swapping two rows of a matrix, multiplying a row by a scalar, and adding a multiple of one row to another row. That's how we perform the actual elimination, right? And we denote all of these basic matrices as EI, the elementary, or I think it's just called elementary matrix for short. And already before, when we talked about LU decomposition, we discussed that these are actually invertible. They are very, very simple, very sparse, invertible matrices, right? And then the conversion of an arbitrary matrix to reduced row echelon form, I can write simply as matrix multiplication, because it's a sequence of elementary row operations, right? And that corresponds to matrix multiplication. So first I do operation 1, then 2, then 3, and so on, until I get it to reduced row echelon form. Right? The same idea as in LU decomposition. Now it's encoded in the matrix language. So A is the original matrix we started from, and E are the elementary row operations. And R is in reduced row echelon form. Okay? And because we can invert all of these, and now you know how the inversion works, right? So I can write all this thing as E, and then this becomes EA equals R, and I can, because all E's are invertible, so E inverse, that's what we were saying the last time, is E1 inverse, E2 inverse, and so on, to En minus 1 inverse, and En inverse, right? So the order flips. But because all these inverses existed, then of course I can multiply them together and inverse of E exists, obviously. So I can write the original matrix A as the inverse of E times R. So this is like sort of like the analog of LU decomposition, if you will. But I don't think it's usually called like that. So those are elementary row operations. I can also do the same thing on columns. The only difference will be that here I will be applying actually the same matrices but from the right. You have seen this before when I apply the elementary row operation on the left multiplication corresponds to operations on rows, and multiplication from the right corresponds to operations on columns. So that's exactly what we can do here. And I need to finish here. But the idea is the same. Okay, so our Lifang will resume on Monday and we'll explain you the rest of this. Okay? Any quick questions? Okay, thank you.